Hello, everyone. Welcome back to another one of Chegg's Linear Algebra Office Hours. My name is Joe, and I'm very excited to be here with you all on behalf of Chegg to give you this office hour time. I am a fifth-year PhD student in NYU, and I'm studying mathematics there. And I've TA'd for several classes, including linear algebra. So happy to be here for this hour, 7 to 8 Eastern time, to answer any of your linear algebra questions. Today I have a few prepared questions focusing on roughly what I think a class will be going through right now. So I'll be going over solution sets and how to describe them for matrices, but you are always welcome to ask any linear algebra questions you'd like in the chat, and I will be here to answer them. So we can get started right away. I have my first question that I prepared on my whiteboard here. And even though this is linear algebra, it's going to have some geometry in it, because being able to visualize things in 2D or 3D will give a lot of intuition for a lot of concepts in linear algebra. So we have the first question is very simple. May not even qualify as linear algebra. Actually, let me use my laser here. So we have x plus y equals 1 as a set in R2, and we would like to describe this geometrically. And actually, what I'll do is, for all of these questions, I'll try and just draw a graph of them to make it even easier to visualize. So for this question, okay, we have in R2, we have that x plus y equals 1 is, we know how to graph this from algebra, and this is just a line. And in fact, let's try and draw it accurately. You can visualize it. We have what is this? This is x plus y. So it looks like the line y equals x, but it's going through this point shifted up by 1. This is A. Okay. And then for part B, we have x plus y equals 1 and a second line, x minus y equals 1. Actually, before I draw this, maybe you have a guess as to what the intersection or what the solution set to both of these equations looks like. If you do, you can type it in the chat. I'll give a few seconds people to think about this. 5, 4, 3, 2, 1. So perhaps you've guessed that the intersection here, you have two lines, so the solution set will be a single point. And let's draw it again, just so we have a visual. We have x plus y equals 1 here. And then we have x minus y equals 1. This should look like something like this. Is that right? Oh, maybe actually should be actually this line, right? Let's see. X plus y equals 1. Actually, I guess the first line was off. So this should be sorry. So this should be this line. And then this line. Okay. And then so for C, what we have is, again, we have 2 lines in R2, but then, so since we have 2 lines in R2, we might think that the intersection is again a point. But if we try and draw this, we see that the first line, x plus y equals 1, we get something like this. We get this line. And then, oh, actually this, right, so. But then if we look at the second line, 2x plus 2y equals 1, we would end up getting a parallel line, right? So this, we can divide by 2 to make it easier to visualize. And we would actually get a second line that's parallel to the first line. And so the point is that, okay, it seems like if I give you 2 equations in R2, it should be obvious that the intersection of 2 lines is a point. But here we have a special case where the 2 lines are parallel, and so they never intersect. Okay, so this is obvious, of course, but now let's move into 3D and try and deduce some more general topics of linear algebra from this property. Also, there's a question from TikTok. Can you explain the second theorem of calculus? So this time is going to be dedicated to just linear algebra, but there will be a different Chegg session, a different office hour this week, which will cover calculus. And that would be the time to ask about the second, I assume, fundamental theorem of calculus. And if you want to find the whole course schedule for this week, you can scan the QR code in the upper left corner for you guys. So you can scan that QR code and get the whole schedule for this week. There will be office hours for probability, for calculus, for trig, and not just math, for organic chemistry, for economics. Hopefully, whatever you need help in, there will be an office hours for that. So you can check the course schedule with the QR code in the top left. Okay, so going back to my example here, I have, I want to describe a solution set to the equation z equals 0 in R3. And so R3, I'll draw like this. This will be my z-axis, this will be my x, and this will be my y-axis. Okay, so any guesses as to what the equation z equals 0 looks like in R3 as a solution set? I'll give you a few seconds. Type in the chat if you have the answer. 5, 4, 3, 2, 1. So z equals 0, let me get another color here, will be the whole plane that is, if you imagine this is like drawn on a table or something, this will be like the whole flat plane that I've tried to draw in blue here. And so actually the point I want to emphasize here is we started in R3 and we have one equation. And so the solution set gets knocked down by one dimension, right? So we started with R3 and now the solution set is 2-dimensional. So let me write that actually. So I'll say solution. solution set is two-dimensional. Now, how about if we add a second equation? Here we draw again z, x, y. Okay, so z equals 0 is still the same plane that we drew. And now I also have a second equation, x minus z equals 0. So this is again going to be a plane. And I'm going to try and draw in 3D. It looks like this. Right, because it's the line x equals z, but then y can be anything. And so the intersection is right here, which I'll try and draw. I'll try and highlight. And so here the intersection is a line. So the solution set is a line which is one-dimensional. And so we started with R3 here, and now there's two equations. And so those two constraints each knock down the solution set by one dimension. You can think of it like that. And so any guesses as to what the solution set for part C would look like when there's three equations? Well, the pattern still holds. With three equations, the solution set will end up being a plane, or a point, a single point. So actually, instead of redrawing the picture, I'm going to draw it on top of my picture for part B. Here I have y equals 1. Let me pick another color. So that will look like this. And so the intersection will just be a single point right here. So this was for part B. And then for part C, we have solution set is a point. And you can think of this as a zero-dimensional object. And so the point is that if you want the solution set to a system of equations, you can start with the whole space, and you can think of each equation as knocking down the dimension of the solution set by one. So of course, if you have no equations, then your solution set is just the whole space. So in this case, in this problem, it will be all of R3. Whereas if you have a single equation, as I've drawn in blue up here, the equation will just be one dimension lower, which is a plane. So a plane is a two-dimensional flat object. Whereas when I add another constraint, another equation, it goes down from a plane to a line. And then when I add one more, then it's a single point. And this always holds, except when we encounter a situation like having parallel lines. And so we want to apply this to solving questions about matrices, except how will we know if we're in a situation where we have parallel lines? where we're not knocking down the dimension by 1. So this is something to do with looking at pivots. And we can go into a question about that. But before we do, I'd like to just take a pause and see if there's any questions that you guys have in the chat. If you guys have any questions that you want help on from homework or from lecture, you can feel free to type it in the chat. Otherwise, feel free to let me know where you're coming from, or if you're taking linear algebra in class right now, or what you're studying in college. Let me know in the chat. Okay, let's go on to the next question I've prepared, which now will start to have more of a linear algebra flavor. So describe the solution set to AX equals 0, where A is the matrix 1, 2, minus 1, minus 2, and 2, 4. Okay, so to do almost 80% of the questions in linear algebra, one of the first steps is going to be to do a row reduction. So we'll do that. We start with 1, 2, minus 1, minus 2, 2, 4. And we like to do a row reduction. So I want to eliminate this entry in the second row. So I'm going to take the second row and subtract twice the first row. And I get minus 1, 1 minus 1, 2. And here I just get 0, 0, 0. So of course I prepared the problem. So this is the result. And okay, so you can read off that what dimension the solution set should have by looking at the number of columns with no pivots in them. Okay, so we can circle all the pivots, and here it's just this one. And so what we see is that this is a pivot. And so both these two columns are not pivots. So these two columns are what we call free variables. And so the number of free variables here is 2, and this corresponds to a solution set being a two-dimensional object, which is a plane in this case. So here we have 2 free variables corresponds to two-dimensional solution set, which is a plane. Okay, so just a few remarks about this question. Oops, sorry. Let me move like this. So let's write out what this equation actually is. We have here a matrix equation, and let's write out the equation that it actually corresponds to. So we'll do this in another color. Here we have, if we call the variables x, y, and z, we have x minus y plus 2z equals 0 is the first equation. And 2x minus 2y plus 4z equals 0 is the second equation. And so this is, here we have 3 variables. And so the solutions are going to be in R3. So if you were to graph it, it would be like this. But here we have 2 equations. And so if you went by the logic in the examples up here, we had 2 equations. When we had 2 equations, the solution set was supposed to be a line. This is like each equation knocks the dimension down by 1. So you went from all of R3 down to a plane, down to a line. And yet here, the solution set is a plane. And you can observe that you kind of have the situation of the parallel lines, right? Except here it's more like parallel planes. You see that one equation is just twice the other. And so this information is captured in the number of free variables. So this is pretty cool. Here you have something you can visualize by geometry. The solution set is not what you would expect it to be. You expect it to be a line because you have 2 equations, 2 constraints in R3, but you end up with a whole plane of solutions. And so, yeah, you can identify this like unique behavior by counting the number of free variables. Okay. Let me pause there. Let me know if you have any questions about this explanation or if you have any questions of your own in the chat. So for those who are just joining, this is a live office hours time. I'm just here to answer any questions you have for linear algebra. You can feel free to ask any questions on your homework or your lecture that you found confusing. And feel free to let me know in the chat. All right. Here's another question where we can see the power of counting the free variables. So the question type is the same to describe the solution set to a matrix equation, AX equals 0, when we have this given matrix. And now, this matter of counting the number of free variables to describe the solution is very helpful because here we have, we actually have 4 variables. If you were to write this out as an equation, you would get x plus 2y plus 0z minus w equals 0, minus 2x minus 3y plus 4z plus 5w equals 0, and 2x plus 4y plus 0z minus 2w equals 0. So it would actually be in R4, there's 4 variables. And so, you cannot really draw that. So this is no longer something you can check by just drawing. So, okay, but let's do this problem. So we'll start with row reduction for this. 1 minus 2, 2. 2 minus 3, 4. 0, 4, 0. Minus 1, 5, minus 2. And okay, I'm going to take the second row and add twice the first row to eliminate this right here. And I get, let's see, I will get 0 here. You add twice that, you get 1, 4, and 3. And then 2, 4, 0, minus 2. And then from here, I want to eliminate this 2. I can eliminate this 2 by subtracting twice this first row from this third row. So I get R3 minus 2R1 is 1, 2, 0, minus 1, 0, 1, 4, 3, and then 0, 0, 0, 0. Okay, now I have my 2 pivots will be this 1 and this 1. And so here I have, okay. Well, actually, maybe before that, does anyone know how many free variables there are now based off this matrix? If you know, you can type in the chat. Okay, if you got the answer 2, then that is correct. So here we have these 2 will be pivot columns because of the 1s. So these 2 1s make these pivots. Pivot columns. Whereas these 2, without the leading 1, are free variables. And so the fact that there's 2 free variables just as above means that the solution set here is going to be 2-dimensional, which is a plane. So 2 free variables. Implies here that the solution set is 2-dimensional, which is a plane. Okay, see a question in the chat from TikTok from KJ. Can you explain absolute value on a graph? I would say that's not exactly linear algebra, but I can say something about it because it is related in a sense. Okay, so if you have an equation like y equals absolute value of x, what does the absolute value function mean? It means that for x that is larger than 0, for x that is larger or equal to 0, this is just equal to the value x. And it's negative x if x is strictly less than 0. And so if you were to graph this, let me indicate this is a separate question. If you were to graph this, you can see that you kind of have 2 lines going on here, y equals x and y equals minus x. And so the line y equals x looks like this. And the line y equals minus x looks like this. And so you get this kind of shape for the graph. And actually, the connection to linear algebra here is actually to note that even though this equation, y equals absolute value x, looks linear in the sense that it's not like x squared or x cubed. It's still like degree 1. The graph, you can tell from the graph that the graph not being like a straight line, that this actually makes it not a linear equation. And, in the context of algebra in general, this doesn't fit in for linear algebra. But this is also another time to shout out that Chegg will be having these office hours the whole week, well, each week for the whole semester. And there will be a specific whole hour dedicated to algebra in general. So not just linear algebra, but a whole hour dedicated to that at some point during the week. I don't actually know when, but you can find out by looking at the course schedule in the QR code in the top left of your screen. So you can scan that QR code and then get all the information about when the coming office hours will be for this week. And then there will be a whole session dedicated to questions more like this one for algebra. Okay, let me erase that. There's a comment from Street Bob FXDB on TikTok. Reduce row echelon form. That is right. We'll be seeing that the whole class of linear algebra. Reduced row echelon form will never go away. I can say from week 1 all the way until the final exam, just finds its way to pop up in almost every single linear algebra question, which makes it such a crucial topic. But let me know if you have any questions that you want to see answered here. Just to pause again, this is a linear algebra office hours with Chegg. So I'm here to just answer any linear algebra questions you may have. Feel free to ask questions from your homework or from your lecture, or you can just comment in the chat if you want to see something about a specific topic in linear algebra. Yeah. Okay, so actually next, I want to continue on this example, which is not just to describe the solution set, but to actually compute the solution now. So let's make this a part B of the question. So this is part A. Let's make a part B. Compute the solution. There's a comment from Damien Dragon on YouTube. Can you help me with a diagram? Oh, a plant cell. Well, I don't know if that will be part of linear algebra, but you can check in the Chegg course schedule, which is in the QR code in the top left, whether there's a biology office hours coming this week. And if so, then you can pop in there and ask your question in that chat. But unfortunately, I am no expert in biology, so I cannot help you with that question. Okay, so let's build on with this row reduced form that we've written here. We have 1, 0, 0, 2, 1, 0, 0, 4, 0, minus 1, 3, 0. Actually, I was a little lazy and did not completely get it in reduced form because of this 2 right here. Remember, for reduced form, you want the columns with the pivots to just have this single 1 as the entry. So this column is okay. Everything else is a 0. But in this column, we want to turn this 2 into a 0. And so let's do that by taking the first row and subtracting twice the second row. And then we get, okay, so nothing else changes. And we get -8 and -7. And so here's, from here we can write out the equations of what this relates to now. We get x minus 8z minus 7w equals 0, y plus 4z plus 3w equals 0. So the way I like to do this is to move all the free variables to the other side. So just rewrite this. And we get x equals 8z plus 7w. And y equals minus 4z minus 3w. And what you can also write, what is commonly written, is to say that since z is a free variable, it can be any real number. So we usually denote that just by writing z equals z. And same thing with w. W equals w. So this indicates any real number. And then you can either be done here. So this is what's called a parametric form of the solution. Or you can also write it, I'll move that away from the text there. Or you can write it in a vector form. Actually, let me move this question down so I can do that. Is that how you do that? Okay. So how would I write this in a vector? So this is parametric form. So the way to write this as a vector form is to group all the variables of the same ladder together. So here I have z, 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 nothing here, but what I'll do is I'll take all the z's and I'll write z times 8, minus 4, 1, and 0. So nothing in that column, nothing in the last row. And then for w, I have w times 7, minus 3, 0, and 1. And so this is what's called a parametric vector form of the solution. Since, okay, on the one hand, it's parametric in the sense that I can I can set z and w to whatever I want, but then there's also these vectors. And so this this form would also help you to visualize the solution. Well, okay, this is a bad example because it's hard to visualize a vector with 4 directions. So a vector in R4, I can't really draw this, but if you imagine this was in either 2D or 3D, and I could write the solution not just as some plane, but actually as a plane in the direction of two specific vectors, then it's something that you can actually graph. So, okay, to summarize, if you have a matrix equation like this, AX equals 0, where you're given the matrix, you can first get the general geometry of the solution just by counting the number of free variables. So the number of free variables is exactly equal to the dimension of the solution set. So that means if it's 1, it'll be a line, and if it's 2, it'll be a plane. Whereas if you want the actual solution, you have to continue doing the row reduction, and then you can get a solution like this in parametric form or in parametric vector form in this way. So I'll pause there. For those of you who have just joined us, welcome. This is Chegg's live office hours for linear algebra. You can feel free to ask any of your linear algebra homework or lecture questions in the chat, and I will do my best to answer them. You can also feel free to ask any questions about any of the example problems I'm doing on the whiteboard. Okay, so another question I have is on a slightly unrelated or a slightly different topic. I should not say unrelated because it's very related, which is the matter of linear independence. So here I just have a set of vectors, 1, 1, 1, 1, minus 1, 2, and 3, 1, 4. And I have the question, is it linearly independent? And so let's try to answer this question. First of all, we can recall what it means for vectors to be linearly independent. So here's a refresher. So if I'll just write the definition with 3 vectors since I have 3 in my example. If I have 3 vectors here, they are linearly independent if the only solution to C1 V1 plus C2 V2 plus C3 V3 equals 0 is the single point C1 equals C2 equals C3 equals 0. Okay, so how do we do this problem? Well, I want to do this in a way that will tie it to the questions that I've done above. And so I can write this equation here in the form of a matrix. So this equation here I can rewrite as a matrix with the column V1, V2, and V3. And then writing AX equals 0. So, okay, I should maybe rearrange this. So I mean that I can rewrite that equation as ax equals 0, where A is the matrix formed by putting the vectors in as the columns of my matrix. So, okay, let's see that in an example. So does anyone know what I would do to get the matrix A with these vectors? With these vectors right here. If you know, you can let me know in the chat. But the procedure is what I just mentioned. So I can put them together in a matrix. So here A will be equal to 1, 1, 1, 1 minus 1, 2, 3, 1, 4. And so, okay, now I just want to check. I have here this equation, ax equals 0 with this as A. And I want to check if the solution is just a single point. And so this falls into the same category now as the previous types of question we were doing above, where we had ax equals 0, we were given a matrix A, and we could describe the solution set. And here we want to know, is the solution set just going to be a single point? And so if that's the case, well, here we're in R3, and we know that the number of pivots is equal to the dimension of the solution set. So the number of free variables equals dimension of solution set. So for the solution set to be a single point, that means we want this number to be 0. You should think of a single point as just a 0-dimensional set. So if we want solution to be a single point, then we need the number of free variables to be 0. Okay, so let's do another row reduction. So as you can start to see in this class, most questions will be involving a row reduction computation. So here we start with 1, 1, 3, and to eliminate this 1, I'm going to subtract the row from the first row from it. So I have R2 minus R1, and I get 0, minus 2, minus 2, and then 1, 2, 4. And then to eliminate this row, this 1, I can subtract R3 minus R1. So the first 2 rows remain untouched, and here I get 0, 1, 1. And so, okay, I can divide this second row here by minus 2 to get 1, 1, 3, 0, 1, 1, 0, 1, 1. And then finally here, I can subtract the third row minus the second row to eliminate this 1 to get 1, 1, 3, 0, 1, 1, 0, 0, 0. So here I have a pivot here and a pivot here, but this entire row became 0. So there's no pivot in the last column. There's nothing here, which makes this a free variable. Oops, let me do this like this. So this column becomes a free variable. And so does that mean that the columns are linearly independent or not? You can check back above here. And so here we said if we want the solution to be a single point, then we need the number of free variables to be 0. But here we have one. And so that means, okay, let's see. What does this mean? Let's connect this back to the previous problems. Here we have one free variable, which means that the solution set will be a one-dimensional object, which is a line. And namely, not a single point, which implies that the original vectors are not linearly independent. And okay, so I wonder if you can see this by graphing it, because there's also a geometric interpretation of the meaning of linear independence, or the lack thereof. And okay, let's see. But it's a little hard to draw things in 3D, so we'll see. So, okay, we have the vector 1, 1, 1. That is not an easy vector to draw, but okay, let's say it looks like this. The point 1, 1, 1. And then we have 1, minus 1, and 2. 1, go. 1 and 2. Okay, actually, this is, I realize it's not easy to draw in 3D. Okay, well, maybe I will illustrate this point with a simpler setting then. Well, actually, maybe let me just say in words, since we're starting to run out of time. So the geometric interpretation for linear independence is that the vectors should all be pointing in separate directions. But okay, that doesn't have much meaning, because if I pick 3 different vectors, they're always going to be in separate directions. And so what I mean by that is that if you look at the lines, if you extend the lines for each vector, then for if I take 2 of them and I were to draw it out, so this is not what those looks like, but you can imagine the situation is like this. If I take two of them and I draw the plane that goes through them, then the third vector would also be on this plane somewhere. And so it's somehow going along in the same direction as the other two vectors. Whereas if the picture were that they were linearly, so this is like linearly dependent. Whereas if the picture were that they're truly linearly independent, it would look like if you draw two vectors and draw the plane that goes through them, perhaps it will look something like this. But then the third vector would go off in another direction like this. So I hope this helps for a visual interpretation of linear independence. So the point is that it will, if you look at, say, like the first two vectors and you see what plane goes through them, then the question is the third one going to be in the same plane or not? So are we in this setting where the third vector is on the same plane? Or are we in this setting where the third vector is shooting off in another direction? So there's a comment from TikTok from Rimaz EG. I'm doing this in college and I'm losing my mind. Well, hopefully these office hours can help a little bit, but if you have any specific questions, well, actually today we're running out of time, but if you have specific questions for next time, you can feel free to message them in the chat. And I don't have to do my pre-prepared questions. I'm happy to answer any homework questions that you have instead. I think that would be a useful way to use this time. But otherwise, looks like we're pretty much out of time. So just want to give a thank you to everyone who came today for this Office Hours live stream. And just a reminder that we'll be having these office hours for various courses in college level or high school level all throughout this week. And you can find the full schedule by checking out the QR code in the upper left corner. So where it says course schedule. And that will give you access to know exactly when, what subject you need help with, whether it's being covered by these live office hours or not, and if they are, to know exactly when to log on to be able to get your help. So thanks everyone again for coming, and hope to see you again